Jai Hind to all of you. I am Dr. Ritish. I am going to give the lecture on the topic of amplitude shift keying, which is in the subject of communication engineering. So let's begin with the syllabus of the university. The first one is the syllabus we will discuss here. So this is the university syllabus. So this is the topic. This topic is lies in the unit number 5th as in the syllabus we can see here. Right, unit number 5th, and it lies in the uh, amplitude digital modulation scheme. The amplitude shift keying is one of the most important modulation scheme that we have covered here in this lecture. So this is the recommended book that we have. We can take from the library as well. So this one is the Simon Hacken book, the Communication System, written by Simon Hacken, and Principle of Communication System, written by Tom and Schelling. These two books are mandatory to take the help to cover this topic. So I recommend this book, these two books as well. So let's begin the topic amplitude shift keying. Amplitude shift keying, also known as ASK. Right. First of all, we need to understand in which category it lies. In which category modulation it lies. So it lies in the digital modulation schemes, and also binary signaling modulation technique as well. So it is purely based on the digital modulation technique, where we need to understand why we call the modulation technique. So amplitude shift keying, the as name suggested, shift keying. So it shifts the amplitude of the carrier signal in accordance with the instantaneous value of the data, right? So here we need to take the data as the digital data in the form of 1010. Can I say this is a binary data, and we have to represent it by in the electrical signal, like in this way, 1010, right? This is the electrical representation of this binary signal, and this can be achieved with the help of line coding techniques. So we have different kind of line coding techniques, such as return to zero. Different kind of line coded techniques we have. The first one is on off, return to zero, non return to zero, and differential coding, and last one is the Manchester coding. These are the line coding techniques by which we can by which we can represent a simple binary signal into the electrical signal, right? So this is the first thing that we need to understand. So in this digital modulation technique, first we need to represent a simple binary signal into the electrical signal by taking the line coding technique. So I think this one is clear to all of you. So first, we have to understand the thing is okay. Now, the generation of ASK signal. How we can generate ASK modulation? We can say so. It can be generated with the help of simple product modulator. Right? So in the product modulator, first we need to do the product of the simple data with a simple carrier signal, that is AC cos 2 pi FCT. Right? Data could be in the binary form, such as 1 0 1 0, right? How it can be represented with the help of line coding techniques. So in the case of ASK, we have to consider a simple line coding technique, that is on off keying. Use line coding on off keying. What is on off keying? If I have a data of 0 or 1, in the case of 0 it is represented by 0 volt, while in the case of 1 it is represented by positive value, right? So in the positive value, so here 1 is here, you can make it the electrical signal by using the on off keying, on off coding, also known as, that is 1 0 1 0. This is 1 0 1 0, right? So I can say that with the help of product modulator, we can achieve a simple ASK signal, or ASK modulated signal, right? How it can achieve? If I transmit the one with the help of product modulator and by using the production of the carrier signal here. So if you transmit the one, then we have the signal at the after passing through the product modulator is equal to AC cos 2 pi FCT, right? While in the case of 0, it will give you the value of 0. Why? Because we are doing the product of 1 with this carrier signal and 0 with this carrier signal. So we can say that simple, if we have a binary, we have a simple carrier signal, means carrier signal present at the output of the ASK signal, while in the case of 0 there is no signal. So if I draw the waveform of this ASK signal, so what kind of waveform we will have? So we will draw the waveform here, right? So waveforms, ASK waveforms, right? So first we need a data. So this one is on off data, on off signaling data, we can see, right? This one is 1 0 1 0 1, and we have a carrier signal, another carrier signal, that is CT is equal to AC cos 2 pi FCT, right? So I am drawing the carrier signal here. This one is CT and T, right? So I am drawing the carrier signal here. This one is the high frequency signal, that is known as carrier signal. So as per the definition of ASK signal, what we will have at the when we are transmitting the one, so at the output side we will have a simple carrier waveform, but while in the case of there is no waveform of the carrier signal at the output, only one we will have the output waveform. So we can say the S1T means 1 is represented by S1T, 0 is represented by S2T. S1T is equal to AC cos 2 pi FCT, and S2T is 0. So I can say this one is S1T, this one is S2T, S1T, S2T, S1T, right? So I can draw a signal here where this one is ASK signal, right? So need to draw what kind of waveform we will have at the output side, right? So one is present here, then we have a waveform, carrier waveform, then there is no waveform, right? Then we will have again waveform, means carrier signal we will have, again no carrier wave, again we will have a carrier wave here. So you can clearly observe here, this kind of signal we can say this is an amplitude shift king, mean it shifts the amplitude by taking the on off signaling. So if the signal is on, then we will have a carrier signal. If signal is zero, then we will we will not have uh, the carrier signal in the case of zero. So this is the ASK modulated signal here. Now we need to understand the energy of this ASK signal, bit energy of the ASK signal, and how it can be what is the constellation diagram for the ASK signal, and what should be the constellation distance between uh, two transmitting bits at 0 and 1. So from the constellation diagram, we need to understand how much probability of error it can have. So let's begin with the, I think up to this point, the topic is clear to all of you. Now, another thing, energy bit energy, right? Energy of a bit, right? So I presume that for transmitting one, this is a 1 bit duration. I can presume here this is TV. TV is representing by bit duration of 1 bit, right? If I take the Fourier transform of this, we already know that the Fourier transform of rectangular function will always be a sinc function, as I know, right? This kind of function we will have. So most of the energy lies in between the first crossing point. So that's why I am taking only this region to calculate the bandwidth of this pulse in the frequency domain, right? So I am drawing here the main highlighted section, this one. This crossing point, what is the crossing point for the sinc function? This is 1 upon TV, and this one is minus 1 upon TV, and that should be 0. As I know, we are now here the carrier signal is CT is equal to AC cos 2 pi FCT, right? So if I take the Fourier transform of this one, what kind of we have? Simple two impulses we have, plus FC and minus FC, right? So this one is frequency, and amplitude is AC by 2, we can see. This is the spectrum of this carrier signal. If I modulate this carrier signal with this data, so we have S1T, right? S1T. So S1T, if I take the Fourier transform of S1T, these two are modulated with each other. So in the modulated signal of ASK, this is shifted towards the FC plus minus FC because carrier signal changes in accordance with the data. So here we have this on positive side and this on the negative side, right? And this point is plus FC and this point is minus FC. So this FC plus 1 by TV, FC minus 1 by TV. Similarly, we have minus FC plus 1 by TV, minus FC minus 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 1 by TV. So from this we can calculate the bandwidth of the ASK signal. So the bandwidth of ASK signal always be equal to this. This one is the bandwidth, we can say. So FC plus 1 by TB minus FC minus 1 by TB. This one is cancelled out, 2 by TB. So bandwidth is equal to 2 by TB, or 1 by TB we can say is equal to RV. So that's why twice of RV, where RV is equal to, what is RV is equal to bit rate and TV is equal to bit duration, as we have in this, right? This is the bit duration. So this is the bandwidth of ASK signal that we have, right? So from this analysis, the next point, what should be the energy from this bandwidth? This is the bandwidth. Energy we can correlate. Now come to the point, energy of the signal, right? Come to the point, energy of the signal. Now energy. So as we know, S1T is equal to, this is a ASK signal. S1T is equal to AC cos 2 pi HTT, for which when you are transmitting the 1. If you are transmitting 0, then it is 0. So energy is equal to 1 bit duration is 0 to TV. For 1 bit, EV is equal to, represented by EV, 0 to TV, and S1T square dt. This is the energy formula. If you integrate this signal, square of this signal, AC square cos square 2 pi FCT dt. Right? If you integrate this signal over one period of time, you will have EV is equal to AC square by 2 into TV. Right? This is the energy, bit energy of 1 bit energy of the ASK signal. If I find the AC value from this equation, then we have under root twice EV by TV. So at last we can also represent this signal S1T, like we can write this signal in this form also. AC we can write twice EV by TV in terms of energy cos 2 pi FCT, and S2T is equal to 0. This is in the case of if you transmitting 1, and if you transmitting 0, then it is 0. This is the energy, bit energy, right? Now we need to understand what is the orthonormalized function, because if you draw the constellation diagram of this ASK signal, so first we need to understand what is the orthonormal function. So orthonormal function, we can say if the energy of any function equal to 1, then we can call this signal is orthonormal function, right? So as we know, we need to find the orthonormal function first to draw the constellation diagram. So EV is equal to, we can say 1 bit energy is equal to, how you can write it? You need to do the 1 bit duration integration of the S1T. As we know, the S1T is equal to under twice EV by TV, as we know, cos 2 pi FCT and dt, and need to take the whole square of it. So EV is equal to, this is square of EV, we can take it out from the integration, under twice upon TV cos 2 pi FCT. this is square of dt. So this is cancelled out 1. So 0 to tv square of 2 by tv cos 2 pi fct square of dt is equal to 1. So we can say the energy of this signal equal to 1. So energy of 2 by tv cos 2 pi fct equal to 1. So this function is known as orthonormal function. This one is known as orthonormal function, right? So in the constellation diagram, what we have here, in the constellation diagram, so as we know, S1t is equal to under root twice EV by TV cos 2 pi FCT for the case of one transmitting. So I can separate the orthonormal function from this total function. So under root EV under root 2 upon TV cos 2 pi FCT in the case of 1. This is orthonormal function. For S2t, it is equal to 0. So in the constellation diagram always drawn over the orthonormal function. This is axis which is representing the orthonormal function. Square root of 2 upon tv cos 2 pi fct. Right. So for 0 transmitting, that is S2t, this is 0, and for 1 transmitting, S1t, this is 1. Sorry. What should be the energy here? What should be the energy here? Under root EV. So the distance between these two transmitting with 1 or 0 or 1, it is under root EV, that is represented as D12 is equal to under root EV. If I say what is the boundary condition, we need to take the average of these two distances, that is under root EV by 2. If this is the distance, if this distance is to have the probability of minimum probability, what is the relation? It is inversely proportional to D12. If the distance is more, then probability of error is less. If this distance is less, then probability of error is more. This is, I think, this is all about the ASK, amplitude shift key modulation. I think up to this point, all the things is clear to all of you. Thank you.